microphone now. I hope that helps the audio. So now we're going to get into the actual boundary layer analysis that is fundamental for all external flows. So similar to the pipe flow thing where we derived, some u of r for that velocity profile, we're going to do something similar. It's going to be a u of y, but it'll be non-dimensional. We'll have to talk about this boundary layer thickness, which will also derive in terms of the x-coordinate on a flat plate. Before we get into all that, though, I kind of want to go over this concept of scaling, as it's fundamental to how you get these equations. So scaling comes up all the time in applied mathematics. It's used in number theory. It's used in cosmology to estimate very complex, hard problems. So I have a little example of why it comes about. So just thinking about numbers for an example, say you have this algebraic expression. And then you'd have, so say this is something true at, let's say, a time 0, and then you go down the road, and then have more, and you should just think to yourself, well, what really matters in this type of an equation? So say this is now at t equals 1, and then he keeps on going. So then there's another time. You check in later, and now all your numbers have changed again. So you can just query a computer to ask for these numbers, and you notice that this is the case. Okay, these are just numbers that you can understand and see, but the idea is that they're changing over time. So you kind of see, but I think we can all agree that, do we really need these? Do you really care about this last part right here that's only 0.0001 changing, and then at time 2 it did barely change at all. Maybe it jumped up a little bit right here at time equals 8 seconds, but it really didn't matter at all. And that's just inspecting the pure numbers that occur in things like this. Okay? So for engineers, really, those are just the numbers, but really what I was describing are the evaluation of differential terms. So at t equals 1, in reality, I was just describing something like this. Some function, evaluated at t equals 1, that equaled, so this is a differential term, but you're evaluating it at 1. And then the other one was something like this. And then over here, then you just take the function itself. Then that last term, what if it was an a? Okay, so when I was describing in numbers, really, let's say I was just querying a Mathematica program to tell me what my function, take derivative twice of it, and evaluate at time equals 1, it looks like this. Same for this. I know I have some graphic ODE solver, and I said, what's the derivative at time equals 0? It's like this. Same thing with this, and then this one is very, very small. So one thing that you could see is this could be really, really small because this number, a, is very tiny, It could be the case that a is just an extremely small number. So I wrote out instances of time for this example because, in reality, differential equations happen over an amount of time. So, in that simple example, I really was writing out this. Some differential equation that looks like this, let's say. So this is nonlinear. right? Not easy to solve. Okay, but if we have the added information that, like, let's say I know what this number is, I know that it's just incredibly tiny, you get to say, well, let's get rid of that term. Right? And that would let you make a reasonable assumption based on some parameter right here to write down this ODE, right, which is linear, and very solvable. So the whole point of scaling is you're just trying to throw away insignificant data based on parameters that pop up within the ODE. So we go one step further in scaling because we actually know physical quantities of what these parameters are. And that's a fascinating, fun exercise to do, right? Kind of uniquely to engineers as we get to talk about the actual parameters in our ODEs pretty specifically because we can measure things. We can measure the length of the plate. We can measure the viscosity. And those all come into play when you non-dimensionalize differential equations. So let's take this example. I imagine everyone's seen it enough. Right? I think we all remember this system. It's the spring mass damper system. It's got a dash put in there, so you get the full equation. So this has a dash plot parameter B. This has a spring constant K. There's a mass of the block. You could say there's an unperturbed length or equilibrium length at like a distance L. So we know that the equation of motion for this guy or girl got B. That's the equation of motion that governs the motion and dynamics of this block oscillating with a spring and a dash pot. So, right, we have variables, right? Variables being x is a dependent, right? So, sure we all know this, that for the variables we have the dependent variable, which is x, is the function we're trying to solve for, and then you have independent variables, which is time. I can always take a clicker and measure what time is, so that makes it independent. So these other things that you normally don't care about, or right, they just pop up in the solutions, but right, you should think of them as these parameters. Right, and the parameters for this system, right, we have the mass of the block, we have the dash, right, we have the damper coefficient, we have the spring constant, and right, we'll have the unperturbed length. So these are four physical values that I can measure, and I can know a priori, before I try to solve it, I can know what these numbers are before I even try to find a solution to my differential equation. Before I even put it into a computer, I would know what these numbers are and I can calculate them. Much like when you have a Reynolds number, right? What do you always do? You calculate. Right? You can always calculate this thing because I always know the density. I can always guess, right? I can always tell you something about characteristic velocity. There's some length scale and there's this. So these parameters pop up in non-dimensionalization of equations. So let's do that for this system. Let's actually do the non-dimensionalization of the total spring mass damper system. So, right, scaling and non-dimensionalization sort of go hand in hand. Right? Sort of one informs the other, or this one informs that one. So, right, so whenever you do this non-dimensionalization of your governing equations, I could go on and on of why you would want your ODE to be non-dimensional, but right, maybe it's helpful to just go about and just do the steps for this. So we're going to go through and actually just do the non-dimensionalization of an ODE and see how these parameters affect the solution.